Hello, my name is Javier Sanz-Cruzado. I am a postdoctoral researcher at the University of Glasgow, and I'm going to present our paper, Accelerating Cross-Encoders in Biomedical Entity Linking with Jack Lever. In this paper, we shall introduce novel architectures for biomedical entity linking cross-encoders that allow us to improve their training and inference time without harming their performance. Let's start by defining what we mean by biomedical entity linking. If we have a text like the one in the slide, where we have mentions of biomedical concepts like varicella, fever, virus, etc., we might find that each of these mentions could refer to several concepts. For example, varicella could refer to a type of mollusk, but in this case, it just refers to the chickenpox disease. To solve this problem, biomedical entity linking aims to automatically find the entity that best matches the mention in a particular knowledge base. The most common architecture for biomedical entity linking uses a two-stage pipeline. First, a candidate generator, which selects a reduced number of candidate entities for a given mention. This generator is usually very fast, very inexpensive. For example, we could use an n-grams model. And once these candidate entities are retrieved, the second phase uses a more accurate, but also more expensive re-ranker to select the best entity among the candidates. A very common example of model for this re-ranking task is the cross-encoder, which represents the focus of our work. A cross-encoder here is an algorithm that uses a transformer-like base model, like BioMedBERT, and receives as input a text containing the mention and a candidate entity. The cross-encoder just outputs the score for the entity, and then the different candidates for a single mention are ranked by descending score. To do this, the transformer receives a sentence following a template like this, and tries to provide a value to the mask token. This token can take two values. One, if the entity corresponds to the mention, or 0 otherwise. The final score is just the probability of the mask token taking value 1, or other words, of the entity corresponding to the entity represented matching the mention in the text. Cross-encoders are very effective as re-rankers, but they have a serious problem, and is that it takes a long time for them to be trained and to be applied. To show some numbers, we did an experiment on one of the most well-known biomedical entity linking datasets, MedMentions, and we observed the following. When we trained a first stage n-grams model, it only took around half an hour to train. But under the same hardware settings, the cross-encoders took from 6 hours to more than 2 days to train. Although lower in magnitude, as inference is faster, similar observations could be obtained during inference. Therefore, we wonder whether we could accelerate the training and inference of cross-encoders for the task without losing accuracy. Let's see how we can do this. For this, we first review how cross-encoders work. Given a biomedical document, we commonly divide the text in sentences. For each sentence, we observe multiple mentions. And for each mention, we use the first stage retriever to obtain a set of candidates. And then, for each mention candidate pair, we need to run the cross-encoder once. We make a call to the cross-encoder. What is the problem here? For each mention, we do multiple calls to the cross-encoder. And this gets even further for a sentence, because a sentence has multiple mentions. And let's not forget that the document has multiple sentences. And all these number of calls are produced both in training and inference. So we had this idea of whether we could accelerate training and inference by showing the information less time to the cross-encoder, by making less calls to the cross-encoder. And for that, we propose several models. The first is what we call a parallel cross-encoder. If we take the architecture of the cross-encoder, the idea here is that instead of just showing one candidate entity on every call to the cross-encoder, we are going to show all the candidate entities for a given mention. And then we're going to produce the scores for all of them. How? Well, while the cross-encoder uses this template for each candidate, we are just adding mention mass token entity sentences to the input sentence separated by a sep token. With this, the score of each of these entities is the probability of the corresponding mass token taking value 1. Doing this, we can just process a mention using a single call to the cross-encoder. But could we do better? Well, we've said that every sentence can have more than one mention, so definitely yes. Let's see how that works. How can we do that? Well, the thing is that we are going to do some similar trick. If we take the architecture of the parallel cross-encoder, where we only pass one mention to the cross-encoder, the idea is that here we are just going to pass all the mentions within a sentence to the cross-encoder. So we are passing simultaneously all the mentioned entity pairs in a sentence and computing their scores in one call. To do this, we use a similar trick to the parallel cross-encoder where we extend the template of the parallel cross-encoder by adding the remaining mentioned entity pairs. And there, the score for each entity and mention is the probability of their corresponding mass token being 1. With this, each sentence is only processed once. So we have one call per sentence to the cross-encoder. But of course, we can apply this trick further away in the sense that we could process multiple sentences at the same time. For example, we could take the template, add sep token between sentences, and concatenate sentences that way. In the most extreme case, where we are passing the whole document on a single call, we might call these a document cross-encoders. But of course, we can have different subdivisions of a text. We might have a document divided in passages or in paragraphs or something along those lines. And in this case, we can create intermediate cross-encoders that take just a reduced number of sentences. And with this, if we apply the document cross-encoder, we have that each document is only passed once to the cross-encoder in both training and inference, which reduces notably the number of calls to a cross-encoder. But let's see how it works. We focus here on experiments answering 2 different research questions, exploring to what extent the novel architectures that we propose affect the effectiveness of the cross-encoder, which is research question 1, and the training and inference speeds of the cross-encoder, research question 2. In these experiments, we test our model on 4 biomedical entity linking datasets, namely MedMentions and CBI disease, NLM-Chem, and BC5-CDR. We apply a 2-stage entity linking architecture, as mentioned earlier, on which we first apply an Engram's TF-IDF model as first stage retriever, and each of our cross-encoder re-rankers as a second stage. As our baseline, we consider the base cross-encoder, where we have one call per mentioned entity pair. To test this extensively, we don't just focus on a single backbone language model, but we use 3 of them with different context window sizes. We use BioMedBERT with 512, Longformer with 4096, and MotherBERT with 8192. The idea here is that the longer the context window, the more information we can pass to the transformer model at once. Besides that, we use the same configuration for every transformers model. We use early stopping during training. We use the same learning rate, the same cross-entropy loss function, and the same hardware, with 2 CPUs, 16 GB of RAM, and one NVIDIA 4090 GPU. The only thing that we vary here is the batch size. We want to fit the model into a single 4090, so we modify the batch size as it needs so we can fit the models properly. As for metrics, we compare here 3 metrics: accuracy at 1, whether the top ranked entity is the correct one, which is the ultimate goal of entity linking, find the best matching entity, and 2 speed metrics, which is the training speeds, how many training example pairs are processed per second, where example here means mentioned candidate pair, and the inference speed, which is how many inference examples, again mentioned entity pairs, are processed during inference. The reason why we do these metrics is because they ensure fair comparison. For example, in training, different models might run for different epochs, and by computing these metrics, we make the numbers comparable. We shall only discuss here the results of meth mentions for the sake of time, but you can find the results for all of the datasets in the paper. We shall first explore the effect that passing more information has on the effectiveness. As we can see, close encoders provide a notable improvement over the first stage free ranker. But let's see what happens when we add more information. In this dataset, as we add more information to the close encoder and we reduce the number of calls, performance diminishes. However, if we look at the raw numbers, the difference is quite small, between 0.54 loss in the case of the parallel close encoder to 3.5 in the case of the document close encoders. And similar trends occur in other datasets where we observe sometimes that the parallel close encoder even improves a bit the performance of the base close encoder, but the differences are very, very small. Which means that adding more mentioned entity pairs to the close encoders has a limited impact on accuracy, either positive or negative. And therefore, all the proposals are reasonable rankers for the task. Of course, while different datasets can react differently to the parallelism of the close encoders, this is one of our main objectives, which was not to harm the performance with our architectures. But let's see if we manage to improve the speed. Let's first observe the training speed for that, and please note here that due to the different batch sizes, different backbone models are not directly comparable. However, we can observe the trends for every different transformer-based model. So, with respect to the base model, parallel close encoders accelerate training up more than 3 times already. This is further stressed when we use multi-close encoder, which go more than 9 times faster training speeds. And document close encoders even accelerate them more. There is one case where it didn't the document close encoder didn't accelerate it more. We'll explore that later, but similar patterns were observed in the other datasets. And what is more, if I look at inference speed, a similar trend is observed where we accelerate the inference time as we cram more information in one call to the transformer-based model. Again, similar patterns were observed in other datasets, and we found this drop down on speed for the document close encoder for modern BERT. But let's see why this happens. Well, modern BERT, as we mentioned earlier, has a longer context window than the other models. It has double the context window of, for example, a long former. Therefore, we can provide longer strings for the modern BERT model, and we have observed that when this happens, training speed diminishes. When we pass strings longer than 4,000 tokens, speed diminishes a bit. Again, this is still much faster than a base cross-encoder, but we should take into account that very lengthy input strings might hinder the efficiency of the transformer-based model. This is something that we just need to take into account. But in conclusions, adding more mentioned entity pairs to the cross-encoder will increase its training and inference speeds. Let's take care of the very long sentences, but this is what we wanted. We wanted a model that improved training and inference speeds. So to wrap this talk, we have shown that we can accelerate cross-encoders fastly by allowing them to classify multiple mentioned entity pairs at once. Generally, the more information that we add to the transformer, the faster it will be. The less calls we make, the faster it will be. But what is more? Adding more information produces a very small effect, either positive or negative, on the accuracy of the entity linking. So therefore, these architectures are viable in scenarios where speed is fundamental, like online annotation services, where we are more worried about speed than accuracy because we are only showing a very small decrease at the worst case. I would like to thank you for your attention, and if you have any questions, please contact us on any of the links provided in the slide. Thank you very much.